Previously, we set up our FEM to work with animation. There are two simulated meshes that we created. The first was driven by the animation itself, and the second was driven by the simulated mesh. Now we'll take a look at other ways in which this can be performed using attributes that we set on the solver. Essentially, we're going to take a different approach to setting these, and this will be an attribute-based approach. Unfortunately, the documentation for FEM is not the best. Houdini's documentation can be rather patchy, with some of it being extremely good and some of it being extremely poor. FEM is one of the poor sections of Houdini documentation, where all the information is actually there, but it's not particularly easy to find exactly what you're looking for. When looking for the attributes that we need to drive FEM solvers, they will not be in the FEM section. Instead, they'll all be listed on the FEM solver itself. So I'm going to open the help on this node. If we scroll down the help, we'll see that there's almost no information for the solver node itself, but there is a large amount of information on the attributes which are used by the FEM solver. Some of these are used to drive the solver directly. Some of these are multipliers or replacement for parameters in other FEM nodes. For example, if we look at one of our import nodes, we'll see that most of the parameters here align with the material properties attributes. These attributes are actually multipliers for the main parameters within this node. And if we look at most of these parameters, we'll see that they have direct equivalents within the interface. Most of these attributes will be multiplied by these values. This allows you to set a base attribute, and then those parameters would be tweaked on a per point basis using the attribute. However, not all of these parameters are multipliers. If we scroll down further, we'll find the material values. These are used to control the simulation fibers, and simulation fibers are what's actually used to create the simulation itself. You can do a lot with FEM using these attributes. There are numerous attributes here, and it is useful to go through every single one of them in order to understand what they do, but the attributes that we're going to be using for the moment are the target attributes. These attributes essentially coincide with parameters which we have in the deformations tab, specifically those under the target section. They will either affect these parameters, or they will replace them to a certain degree. We can exit the simulation solver and go back to the rigging part of the network. And I'm going to be working on the output deformation. This is where we'll be getting the animated mesh. And at the moment, this is the most basic setup we can have. Essentially, this is a basic way to capture with the rig driving the mesh. What we'll do now is add the target P attribute to this branch. This will store all of the information for these points in an attribute, which will be used to drive the animation. So instead of referring to this mesh or this output and referring to this directly from our solid geometry node, we're going to be storing this in an attribute, and our solver will use that attribute instead. The biggest advantage of doing things this way is that it makes the network more portable, as any mesh using this attribute can be used to drive our simulation. We'll need to create the attribute, and I'll be doing this with an attribute wrangle node. I'll connect this after the bone deform node. This will be the target P attribute, and it will be a vector attribute. So this will start with v at, the name is target P, and we'll set this to be equal to our point position with at P. So this will store our target animation. We'll then take this attribute and we'll use it to drive our simulation. To do this, I'm going to need to reorganize the network. This will be done using a multi-solver. The first input of the multi-solver will be connected to my geometry. After this, I'm going to get a SOP solver. The SOP solver will allow us to update our attributes dynamically. This will be connected to the second port of the multi-solver, and it must be connected before we connect our FEM solver. I'll connect the FEM solver after this. I'll make sure that this solver no longer has anything connected to its input. I will not reconnect the constraint yet. We can now use the SOP solver to transfer information onto the geometry which is coming into the network. I will enter this node. The first path here will be setting my geometry. I will add my target P attribute to the geometry here. I'll do this using an attribute copy node, and this will be connected to this branch. I'll need to connect the second input, and for this I'll get an object merge node. I'll select the animated mesh in this object merge node. I'll specify that the attribute I'm copying is the target position. And this should complete the base setup. So now the attribute has been added to our geometry, and we are updating this attribute dynamically in the network. Now we can look at how this affects the solid object node. I'll be working in the deformation tab. Here we're going to turn off our target deformation. And our deformation should still be working. It will now be getting the animation from the attributes rather than through the reference in this node. The next of the attributes will be target strength. This will be followed by target damping, which will work in the same way as target strength. So I'll only look at target strength for now. The target strength attribute does not directly control the target strength parameter. Instead, it is a multiplier for this parameter. And this means there are a number of ways we could implement this attribute. I'll exit the DOPS network. I'm going to add the attributes directly to the simulation geometry. I'll add an attribute wrangle node here. This will be a float attribute and it will be called target strength. I'll add a slider so we can control this attribute. This will be done with the CHF function. The label will be target strength. I'll leave this at 0 for the moment. If I reset my simulation, we'll see that the simulation is still running and that this multiplier currently is having no effect. This is partly due to how high my default value is within the network. When my target strength has been set to be this high, multiplier attributes will usually have no effect. So I can set this to a low value. If we resimulate now, we'll have a far smaller effect of the stiffness on the mesh. If I raise the value by a small amount, we'll see that we have some increase of the influence in our simulation. I'll set the influence to be the default max, which is 1,000,000. If I raise the target strength to 1, we'll see that we have more influence. I can also now push this beyond 1, and you'll see that we now have a much stronger influence. Alternatively, I could set the base target strength to just be 1, and we can use the target strength to set a very large value, and this kind of approach can work as well. So you can tweak these influences in whichever way you're comfortable, and you can be reasonably flexible in the approach which you take. There are, however, a couple of other ways of connecting the animation. So in this case, I'm going to set the target strength to 0. In the main network, I'll set the target strength attribute to be 0 as well. I'm going to be adding another attribute over here, and this attribute will give us another way of controlling our animation. The name of this attribute is pin to animation. This is an integer attribute, but it is a Boolean attribute, so it should only ever have two values, 0 or 1. I'll prefix this with I@. I'll set this with an integer parameter, so I'll use the chi function. I'll call this parameter pin to animation, and I'll add it to my attribute wrangle node. I'll set this parameter to be 1, and then I'll resimulate my network, and we should see that we get a reasonably accurate simulation here. This is because the animation is now directly driving my simulation, and there's no weighting involved now. So this is a more direct way to drive the animation. If I set this value to 0 and resimulate, we should now no longer have any animation. So if we just want animation to drive the solver and are not looking to simulate it specifically, this is a very effective way of doing that. This is not the only way of doing this. We can do the same kind of thing in a different way. I can enter the network. I will get an FEM target constraint. In the target constraint, I'll set this to be a hard constraint. And the object that we're constrained to should be the animated mesh. So using the target constraint would be another way of attaching our animation. So that's how we can use attributes to drive the animation. We could also use the pin to animation attribute, or we can use the target constraint to drive our simulation with an animation.